Yeah, let's get started. We're just at time now. Yeah, I don't have the camera, so I'll just stand back here. Yeah, thanks for joining us. It's our second below sea level. We're going to try and do this again, the reminder, the first Tuesday of every month. This is me and Aaron putting this together. Yeah, we're still looking for someone to do next month's talk or the month after. Basically, any first Tuesday of the month, you're free. Let us know. If not, then you'll hear from me. I'll talk about WebAssembly or something. Yeah, also, one other thing. This is sponsored by a company called Dilibso. We're sponsoring the pizza. Talk to me about jobs and stuff like that, because we're hiring. So thank you, Uncle Dilibso, for the pizza. Yes. Yeah, and that's it. Do you have anything to say before you start?
No, I've got
any business? Okay, well, we're just gonna get started. So today, Aaron's doing a presentation on Maglev. So get started.
Ooh. Awesome. Hi everyone. So start with a quick. Oh no, I've got that one. There we go. All right.
Good.
Yep. I just have advanced slides instead of adjusting your stream. Hi, I'm Aaron Lee. I've been a software engineer for 20 years or so, SRE, kind of bouncing back and forth between those. Worked at places like Rackspace, where I was a core committer on OpenStack, was at DigitalOcean, was at Fastly, I've been on a few other smaller, no longer existing startups. It's my email address. I'll have it again at the end if anyone wants to contact me. That's the best way. Love chatting about this kind of stuff. And if you want to give a talk here, please hop up. It's awesome. As everyone saw, the name of this was about Google's load balancer. And anytime you say Google in the name of something, people say why do we care? Which is a legitimate question. Google has problems that the rest of us don't have, unless you're a very specialized, focused in on this one piece of the field. Which we'll see later. People who worked on this were obviously very focused in on networking and load balancing. But learning about how Google solved this problem, we're going to talk about. There's kind of two halves of this talk. One is, what is load balancing? How do we address that on our scale, on a smaller scale? And then where does the edges of that, where does it fall apart? And then when we look at how Google solves the problem, we're going to look at a lot of how the internet works, how web servers work, which shows up some of the really cool solution they came up with, which at the end of this, it's a cool paper. So talk about that. So first thing to start off is just what is a web request? And when I say request, I don't mean just you type in a URL and hit return. That involves a whole lot of communication between you and a web server. You're not just sending one packet and getting back one response. It's a whole stream of packets, and within that could be multiple different actual HTTP requests. If you're now with the HTTP 2, I think it was, that it introduced pipelining, so you can have one TCP connection that has a whole bunch of requests within it. You can have a quick HTTP 3, which another Google project, we can talk about that another day, but that's based on UDP. And you still have this situation where you're trying to get a whole bunch of packets from the client out to the server. The server's going to do some kind of processing and spit back their response. And of course that takes up resources, compute, there's network bandwidth limitations, there's network queues on your operating system is packets coming in, and it's going to hold on to those until it can actually process those. And in the ideal world, you have one client, you have one server, you make your request, serve the page, it's fine. But this isn't the ideal world. We have a whole bunch of clients, and they can make a whole bunch of requests to your one server, which eventually you will back up those queues, you'll be delayed in processing, you're going to have timeouts, you can actually crash the server if you end up overflowing buffers, all kinds of bad things happen. So we get into the question of how do we want to solve that? And the question there, we've got got our little graph here. We've got our clients go through the internet, and we want something that sits in between the clients and multiple servers, so that the multiple servers can handle multiple requests. And kind of one of the first ways people looked at doing this was with our old friend DNS. Everyone knows DNS is always a problem, but DNS can be a solution to things as well. DNS allows you to have multiple IPs in the A records and the quad A records, which the clients have at their discretion to make a request to whichever of the IPs that it gets out of the DNS request, which does allow some sort of balancing between your service, but there's a couple problems with that. One, you have no control over the clients, so they could all just, Mozilla could just, we're just gonna pick the first request, and now all of a sudden you're right back to the same problem of one server getting all the traffic. You also have the issue that DNS takes forever to propagate. Forever being in the terms of, we deal with milliseconds to web service, and that can take minutes or hours for DNS to propagate. So if you have, you want to add a server, remove a server from rotation, your DNS records are going to take a long time for that to actually propagate. So what if we add a hardware load balancer? And this is kind of talk about like, what is a load balancer? A load balancer is just a really beefy machine that does as little processing as possible, take packets in, and map them from a client to one backend machine. So we talked about before, a request is multiple packets. It's like a connection. So you have, if you get packets and you spread them across machines just evenly, you're gonna break your connections. You're not gonna be able to actually decrypt to TLS or anything, because that's gonna spread across multiple packets. Anyone uploading something that's more than 1,500 bytes, you're going to have it'll be multiple packets. So you have to track the connections that come through. So you're going to be, as a load balancer, you're getting a whole bunch of packets coming in, and you have to know, hey, this packet from this client is going out to this backend server I'm sending to. And so that's where the complexity of load balancer comes from. It's not just spreading requests around, it's tracking the connections within those requests so that people don't break them. You can then get into other fun little benefits, like if you want to remove a server from the backend pool, you can tell your load balancer, hey, we want to stop sending new connections to this machine and let it drain out all the connections that exist before, which is super helpful if you're trying to, say, redeploy your application and you don't want to just cut all the connections that are happening right now and just 500 out all those people. No, you want to service let those connections finish, let them drain out, and remove them. And that's load balancers what'll let you do that. This adds in here a little closer. You end up with these other issues, like what is the algorithm you're going to use to spread connections around. You have issues. What if some connections that come in are really expensive to process, and other ones are really cheap to process? Like you got a web server, you have some that's streaming video or something that might be a long-running connection that has a whole lot of data in it, and the others might be just simple 200s it's responding to. And if you put all the long-running requests on one machine, you're going to overload that machine. So now you have issues like you need to have some kind of back pressure from the machine to be able to say, hey, look out, I've stop sending connections my way. Like there's a lot of different algorithms and a lot of magic that gets into how do you spread load across a cluster of machines in such a way that you don't kill those individual machines. As everyone has noticed with this thing, we still have this problem on the left here where there's one arrow. So when you have one hardware load balancer, it's still a single point of failure. So we've alleviated some of the problem with load, but we haven't alleviated the single point of failure. So these load balancers are, they're super expensive. They can be, really beefy machines. And the people who sell you these beefy, expensive machines, their solution to reliability is to sell you a second beefy, expensive machine. And this does some really interesting things. So to understand kind of how this works, we have to think about IP addresses. People think of an IP address as being the address of a machine on the network or of a single interface on the network. But in reality, an IP address is just some direction in the network that you are sending traffic. So when you have two machines, two load balancers like this, a lot of times the way they work is with something called a virtual IP. So the load balancers will advertise to the switch. Both of them will say, I'm serving, this MAC address is serving this IP address, which in most cases, if you have a switch that doesn't understand the fact that you have load balancers behind there, you're going to end up flapping back and forth between these two connections. But if you have a switch that understands the load balancers and the load balancers are able to advertise to the switch will send the same traffic down both of these network connections to both of the load balancers. And in this case, you can't have both load balancers responding to traffic. They have to coordinate somehow to know what's going on. So most of the time what happens is you have one load balancer being active and the second one being a failover. And the failover load balancer is monitoring the health of the active load balancer. And it uses a protocol, and it's called STONITH, which stands for shoot the other node in the head. And literally what it does is it sends a packet up to the switch and says, shut off traffic to the other guy. And it will stop that other load balancer from acting, and your backup load balancer takes over. This usually works sometimes. When these things are deployed in a high load situation, sometimes what happens is whatever conditions cause the first load balancer to fail will cause the second load balancer to take the first one out of action, and then all the traffic comes to the second load balancer and just falls right over, and then your CEO calls you and you're in trouble. So those are hardware load balancers. They get very expensive, they get very large, but they're still limited by the size of the upcoming stream. Yes?
If you were to have your load balancer set up that way, when they do that switch over, does the one that was originally passing all the traffic become your backup now, and this one's now your main one, or do they eventually try to go back to?
Yeah, so the question was, when the failover, do you automatically fail back? And I don't believe it's, in most cases, automatic. All the F5s and the devices I've worked with is a manual failback, just because you don't know what conditions caused it to break. But that's, yeah. Again, it's been a while since I've dealt with these hardware load balancers, so good question. Cool. Yeah, so hardware load balancers are fascinating, and there's another thing, kind of an intermediary stage between what we used to with hardware load balancers, and what I'm going to describe with the Google thing, and that is cloud load balancers, which essentially is the software for a hardware load balancer running in the cloud. Yes. So Amazon did this for a long time. Their load balancers were managed squid, basically. You had an instance that was running your load balancing software, but it was just a EC2 instance, the same as any other. So it's still limited by the bandwidth available to that instance. But it also had the benefit of it's very easy to move IPs between. Just you're dealing with a software-defined network, so you can go. This interface is now over here, route traffic over there, and you also have benefit of being able to spin these things up very quickly. You're not dealing with hardware, so it's limited as how fast you can boot up the new load balancer. So you can have fairly quick failovers, but you still, so you get the benefits of having this machine that's able to track all the connections. You have the ability to be able to push back with your algorithms and say, I want more traffic on this machine, less traffic on this machine. I want to be able to drain this machine so I can replace it from service. You can do things like one of the big problems that I'm sure we've all heard of in the distributed system is called the thundering herd problem. So when you have, let's say you have 6 machines, and your load gets to the place where causes one of the machines to crash. What happens to all the load that machine was it gets balanced across the remaining 5, which probably will cause one of those to crash, which then on and on and on until all of your machines die. So you can have this situation where you end up with a whole bunch of traffic spike. Oprah tweets about you or whatever, and incoming traffic, it takes down all your machines. Smart load balancers can actually shed traffic for you. And so you can say, I want to limit a certain number of requests per backend node, just to prevent that thundering herd from taking out your entire system. So some people do get 500, some clients don't get service, but you're still up for some definition of being up. And so that's one of the benefits of having a smart load balancer sitting there. Is it gives you a lot of control over what a lot of control over the traffic that is heading to your backend nodes. So we kind of covered where load balancers are, or where hardware load balancers and where the old way of doing things was. So let's go out. What about Google Scale? So we talked about there's that issue with there being so much traffic that it overwhelms any one network link. Like, you can whatever speed network link you want to name, Google has more traffic than that. Like they multiple routers, the traffic. So how do they address this situation? And they don't want to buy more and more expensive machines, right? That's the Google philosophy of hosting, is you want to use commodity hardware, you want to scale out instead of scale up. So scale up is buying more expensive things, buying a bigger thing. Scale out is being able to use more things that are cheap and commodity-ish. And the other thing about this is that you have redundancy beyond n+1. So when you have the failover node there, you have one extra node that you're going to fail over to. If they both go down, well, you're screwed. Now, if you have, your entire Google fleet of servers, you can use any of them as a load balancer. This really increases the redundancy that you have available. So Google was kind enough in Usenex 2016 published this paper that kind of explains how they addressed this problem. It's called Maglev. They've been running it in production since 2008, which is interesting to know that there's a lot of ideas in this that have existed prior to the way that Maglev put things together, but there's some interesting ways that they actually handled the load balancing itself that makes this more able to scale in a way that other systems haven't. So one of their big issues was being high performance. So every node, they don't want to waste that bandwidth. So even in 2008, they were able to stream at line speed from every web server, which I think at the time was 10 gig links, and 40 gig links are pretty standard now, and I assume they're able to saturate those as well. Part of the way they're doing this is they're not inspecting any of the connection. As you'll see later, they're not like trying to figure out what endpoint you're going to, or what kind of or what kind of what service you're trying to reach or anything. It's completely based on the information available in the packet header itself. One of the other big things with this was connection persistence, so that the way they described that is packets belonging to the same connection should always be directed to the same endpoint, which is, you think about it, like that's natural, but like that is one of the hard things to do when you're, it's like, how do I know, this client is talking to this machine over here, and maintain that idea of connection across a distributed system. So we'll give a quick overview of kind of how this works. Sorry, I was trying to draw with a keynote. So, but so you've got multiple clients, and they're sending packets to Maglev. Maglev itself is a cluster of machines. These machines are not. They have a. Okay, well, let me back up. So Maglev itself maps virtual IPs we were talking about before to the backend nodes. So the Maglev machines themselves don't represent a single IP address. They represent a network of IP addresses, and they advertise to the router to say, here's the block of IPs that I'm responsible for, and the router, whatever router they're using upstream, Cisco, Juniper, whoever, uses ECMP, which is the equal cost multipath, just spray packets at this cluster, just everywhere it goes. Like it has no concern for the connection, is over here, so I want to send packets to this machine. It just launches them out there. Maglev is what has this mapping in it to go from this packet has come in, is actually going to this specific backend server. The backend servers then use something called direct server return, which is where they craft their response headers with the IP of the service and send it directly to the router. So all the responses don't go through Maglev. It's just incoming traffic, which is a benefit for them, because when you think about when Google's serving like YouTube or whatever, you send a tiny little packet goes in and then a whole bunch of data comes back. So they don't have as much data going through Maglev as you would have if you were a router like handling all the traffic specifically. So the way this happens is, so when you think about the information available at the packet itself, you've got the source IP, you've got the source port, you have a destination IP, destination port, and you have the protocol number. Protocol number being like, it's the field that says like, is this UDP, is it TCP, is it fiber channel, like whatever. There's a gazillion protocols that nobody uses anymore, but that are in the spec because that's how specs work. So all of these nodes have a hash table that they can take this 5-tuple of information from the packet, look up in the hash table where the backend node is, and that gives them, look up in a hash table is, you're very computationally efficient. So you don't have to do a whole bunch of computation to figure out where am I sending this packet. I just look up and I send it to that node. The real magic though is how do you build this hash table, right? So you've got this mapping from incoming packets to destinations. You don't want to use something like Redis to like share this hash table. You don't want to synchronize the hash table across all the nodes because that's it's expensive. It's a point of failure. It's a lot of communication that goes through there. So they use something called a local consistent hashing. So they have an algorithm for where given a state, you can build a hash table from that state the same on any different nodes. You, instead of going, like we think of hashing as hashing from, like you've got a big file and you want to hash and get like your MD5 or something. The local consistent hashing can also build a full hash table from this, your initial set of data. So they can go and they can pre-compute this hash table that in their algorithm, they have ways of adjusting the weights on different things. They could say this machine is going to get more traffic, and this machine is going to get less traffic. But every Maglev node doesn't have to know the state of all the connections that are ongoing. It only has to know the state of the back-end machines that it's trying to map to. And so that's the magic they have here, is that by using this locally consistent hashing, they can not have to synchronize the high-speed individual packets across the entire network. They only have to synchronize the state itself, which you have a 40 gig link, you have packets coming every fraction of a millisecond, but you might be adding or removing nodes on the order of minutes. And so you're recomputing this hash table is much more computationally expensive, but you only have to do it every once in a while. So they've taken this failure point and they've kind of like spread it across the machines. If you have one of your Maglev nodes die, right, your router is going to try and send packets. It no longer has that connection, so ECMP says, oh, just let me use one of these other equal costs. So your router takes care of actually spreading packets around. You're using your just basic routing technology. So if you have 6 routers or whatever, it works the same way as the network has always worked, just to spread packets around this big mass of Maglev machines. And that's really the magic of it. They've removed that point of synchronization from the individual packets, individual connections, and moved it to this like the level of the state. It's like generating the state of the machine itself. So to review the one of the big parts is that ECMP we talked about, so you don't change the routing framework, you don't change the responses from the servers, they don't go through Maglev, and you just have this little section where you're trying to do this mapping. So that's really the magic of Maglev. Yeah, so I guess I assume there are gonna be more questions. There's a link to the paper itself, which gets really into the consistent hashing algorithm, and it's kind of I sort of understood it. I haven't tried to implement it because it's out there, but yeah. So that's how Google manages to serve, like, if you ever do dig Google and you get back one IP address, and you're like, what the hell? How does this work? That's how. So.
Can you
Yeah.
explain the local
sure.
the local hash again? Because is
Yep.
this similar to what databases do? I mean, it seems like vaguely familiar. But I was kind of confused about what you meant by it computes the whole state of the hash table. So it's not a hash function; it's like a whole table of data.
Right. Well, they compute entries for every unseen tuple that comes in. So the tuple comes in, and you compute from this tuple what the backend machine, or what the backend what your entry in the hash table is, and then you have as I understand it, the nodes have ranges in the table where they say, here's where I'm going to be responsible for keys that end up in this part of the table. So sorry about that.
It does sound kind of similar to how databases do.
Yeah, similar to like vector clocks,
Right.
where you have a space that you're responsible for, and like if your hash function lands you in that space, you go like, oh cool, I win. And then as you add and remove nodes, it recomputes the entire space, so that you still,
Right.
but you still end up with connections. Like their algorithm is weird because when you recompute, you still own the same chunks that you did before.
Right.
So that as you have like the connections that are coming in, you're not like dropping connections and spreading packets the wrong backend server. So
Yeah, because databases have kind of a similar problem where you're mapping, like if you're sharding data,
exactly.
you need a way to map to those nodes, but you can't shift all the nodes when one leaves because the data doesn't live there anymore. It's so you need that cache table to be consistent to go to those nodes, but then you might have some kind of I don't know. I've seen the way that people come up with that ring.
The
Hashing.
and it gets weird when you're adding nodes and removing nodes, because you do want to section off data and take over that shard, but it's
A question was what was the name of the protocol? The E something.
ECMP, equal cost multipath, and it's so the way routers work, they they don't look at IP addresses, they look at what network you're sending it to, and they know that through this link I can get to this list of networks, and through this link I can get to this list of networks, but each network has a cost associated with it. I'm using air quotes here, cost. And the cost is just what the router advertises. So every router will then turn around and advertise out its link. Here are all the networks I know how to get to, and here's my cost of getting to those networks. And so the network, in this case the internet, builds up a list of, from every router, here's how I can get to the entire internet. I have this packet, I can send it down this link, and it's going to cost me this much, or I can send it down this other link, and it's going to cost me a different amount. And you don't care how it goes from that. You just pass it down that one link and then let the other router deal with it. So that's kind of the.
And that cost, that's number of hops, or?
No, it's just made up.
Okay.
So a lot of what network operators will do is go in and mangle those numbers based on any sort of thing. So like if you have a peering agreement with someone, so it might be an extra hop, but it could be free to send your traffic that way. Whereas this backbone link is, it's really fast, but it's expensive to use. Or, this one might, they might be a router that goes through some network you're not allowed to go through. If you're, crossing international boundaries or something. Like there's all kinds of ways they'll say.
So it's more like a weight at that point.
Right. It's that's why I was trying to use air quotes. It says cost, but it's it's kind of a made up number. So.
And sorry to hone back in on the.
Oh, no.
What was that algorithm, the hashing function?
Oh,
I guess it wasn't a function, but.
Locally consistent hashing.
Yeah. So, can you explain a little more like that process? Like, if you lose a maglev node, like, and this machine was responsible for a block of IPs, I'm so confused on like how does the next machine like, oh, I own these now, like.
Oh no, so it doesn't. They all own all the IPs.
Okay.
And so when they have that table, because it's computed to be the same on all of the nodes, it doesn't matter which one gets the packet. The maglev machines themselves don't really have IP addresses in the sense of this. I mean, like they have admin interfaces, but they're not like the interface itself isn't ARPing out a single IP address the way like when you set an interface in a Linux machine, like they're advertising what is gRPC, like the routing protocol, saying here's the blocks of IP addresses I have access to the router itself. So the router thinks it's connected to however many hundreds or dozens of other servers, other routers. Sorry.
Gotcha. Okay, so any maglev node can
route any packets. Yep.
Okay.
Yeah, so they don't have any real inspection into the connections going on. They just have each individual packet. So even though there's a connection between the client and between the backend server, but the connection doesn't exist in maglev.
So the maglev is just like another it's like another router almost.
Right.
It doesn't each node doesn't own a set of bandwidth of backend. It owns all of them.
Yeah.
And that table tells what's available. Okay.
Right.
And so they're basically just like you're just replicating that hash table across how many nodes you have.
Yeah. And you don't, and the other magic is that you're replicating it, but you're generating it from data, so you don't have to there's no information about the connection required to generate the hash table. So it's a much slower changing set of data than trying to synchronize synchronize like if they were tracking the connections themselves, like trying to synchronize that would just be too much. Because you do like a SYN attack or something, where someone just floods you with all kinds of data, you would end up with a giant hash table. But because it's computed, they can, they don't have to deal with that. So. Yeah.
Can you go back to the last screen?
Sure. Oh yeah, and the moral of the story is just click the button that says load balancer in the console. Yeah. So.
Cool. Any other questions anybody has?
I have one. With respect to that hash table as it exists, how does it update if a bunch of backend nodes fail? Like, how does that propagate throughout? Is that?
Yeah, they have. They talk about like their configuration distribution, but they do manage every maglev node has the configuration of all of the backend services that it knows about, and so it has that mapping of here these backend nodes have access or are representing this service, and these other backend nodes are representing a different service, and that information is what it uses to compute the hash table.
So if it sees a bunch of failures, it's like, okay, we're not going there anymore.
Exactly. Yeah, and it just recomputes the hash table. Yeah.
Each maglev node will realize that on its own.
Well, it gets pushed that by the configuration system. Yeah. So there is still synchronization that happens. It's just at the configuration level and not at the connection level.
I got an online question. So the IP source field, when it reaches the web server, it means the web server can send replies back to the source IP bypassing maglev?
Exactly.
Yeah.
Yes. That's something that's existed for a while for like hardware load balancers as well, called direct server response. And it's your server, when it constructs the response packet, it inserts that destination IP as the source IP of the response packet and sends that directly to the router or out of band.
So basically it puts the return address as like a PO box.
Yeah,
pretty much, yeah.
yeah.
It's very cool of Google to give us an academic paper on how this works.
Yeah.
Is that like usual? Is the thing? And like how many other other companies do they roll their own maglev? Do we know? Is there anything to compare?
I saw
against?
like there were a couple other companies on the header, right? There's like SpaceX and.
I think those are people who left Google when they
Oh, I see.
like
okay.
between doing the work and publishing the paper. But I do know that through pouring beers into people from other companies, it is fairly common to do something similar to this. The consistent hashing is a uniquely Google thing. So a lot of the CDNs, all of their pop nodes are also, they're running Berg or whatever and responding as router nodes, but they keep a lot of what they're trying to respond to in the cache on the cache node itself. So they don't have to do that mapping step. They just, you send traffic to all these machines and they respond out of their own local cache. But I suspect part of this is also Google just flexing and saying, we have problems no one else does.
So we deal
Sure.
with our traffic.
So they're willing to talk about it because,
There are only.
no one else is
it
gonna.
seems like
yeah.
all the hyperscalers
Yeah.
they're done. There's like
Yeah,
a handful
it's-
of them. That's it.
Awesome. Yeah, thank you all for coming. It's a lot of fun. And
All right, thanks,
yeah.
Stream. We're
Yeah,
we're gonna go
thanks.
get some beers now, and see you guys next
Yeah.
month.
Oh wait, before you click stop, if anybody wants to give a talk next month,
All right,
please.
let's do it. Yeah, come
out,
come
we're-
talk to us.
Yeah. Excited about everything.
We have ideas ourselves. We can pitch you,
Yeah.
and yeah. See you guys later.